Now you want to introduce random variable and expectation, which are two very useful probabilistic tools that we can use. So last time we proved two statements. One is about the Ramsey number, and then the other one is about the two-colorability of a hydrograph. And there, what was the proof strategy? We define bad events. Then we use the union bound to show that no bad events happen with a positive probability. So that's very natural and basic approach in probabilistic method. And what if we are in different situation that we don't have to avoid all those bad events, but if some number of bad events are okay, but we don't want them to be too high. Or in the reverse way, we want some good events to happen at least a certain number of times. So in other words, I mean, we care about how many those events actually happen. So what if we care about the number of events that hurt? So in order to deal with such a situation, we introduced this concept of random variable, which is a useful tool to deal with such a, quantitative parameter which comes from the random event. So we say that random variable, this is on a discrete probability space. Say S. This is a function or function, and usually we write it as like capital letter, say X or Y or G or sometimes other, which is defined on X, F. And usually, if not specified, its range is real number. And if the range is more specifically a natural number, and it is called discrete random variable. And if the range is 0, 1, then it is an indicator random variable. Okay, and as this is a function, this could have certain value. We write this sentence, this equation that x equals k. This denotes the event. So all the events in, say, S, such that the first value is k. So this is collection of events, so we can consider its probability and write the probability of this x being k or its probability. And we say the expectation or its expected value as we write it as this bold E bracket x. This is the expectation of x, and this is you take the all events in f, and then you take the value of this function, and then you multiply its probability, and then sum, and then also, of course, it is when the summation converts. So this is like average. To be more specific, this is weighted average of this function. So you have f, which consists of lots of elements. Each one of them have the value of this function, and then they all have a weight, which is probability. So we take the weighted average. That's the expectation. And one of the key properties that we will utilize about this expectation is that if we know the value of this expectation, then we know that there exists an element of this probability space for which the value of x is as large as or as small as the expectation. So proving this is easy, right? If not, that means all the elements in here has the value of x smaller than expectation. Then from this definition, this is actually smaller than expectation, which is contradiction, because this is the definition of expectation. So this is very easy statement to prove, just follow from the definition of the expectation, but which is also very useful. And we will utilize this to prove, many theorems that we want to prove. And for that, we should be able to compute the expectation. For computing expectation, the following lemma, known as the linearity of expectation, is very useful. If we have a random variable x and x1 to say xk, those are all random variable which take the real value. So they are on the same space, such that x is summation of xi. Then the expectation of x is same as summation of the expectation of xi. And also, expectation of some constant times x is same as constant times the expectation of x for any constant c. Again, proof of this is not difficult by utilizing the definition of this expectation. And it is quite useful when we actually use it. Most of the time, how do we use it is that when we have certain random variable x, which is what we are interested in, what we do is we write it as a summation of xi or some indicator random variable xi. Then for this indicator random variable, expectation is easy to compute, because if you use this definition, this number is either 0 or 1, because this is indicator random variable. For the elements A, which make it 0, we just forget it, and then the ones make it 1, then this is exactly the probability that the xi is exactly 1. And once we compute this, then you use this linearity of expectation to compute the expectation of f. So that's usually how we use this linearity of expectation to compute the expectation. So Now we use this to prove the following theorem by alone. So he showed that for some constant C, so there is this absolute constant C, which doesn't depend on any property of this G. Every graph G with average degree D has least chromatic number. At least C times log D over log D. So, what does this theorem tells? This theorem shows that the chromatic number and least chromatic number has a completely different behavior. They are quite far. Why? I mean, for chromatic number, we know that say KNN, it has average degree n over 2, but its chromatic number is only 2. This is constant. So you can find a very dense graph with lots of edges. So by letting n goes to the infinity, this has huge average degree, but the chromatic number could be bounded. But what alone proof here means that if your graph G has large average degree, then its least chromatic number also must be large. So in some sense, this chromatic number depends more on the structure of graph rather than its denseness. But the least chromatic number, even if your graph is very well structured, as long as there are many edges, and its least chromatic number should be high. So it shows that these two parameters are fundamentally different in this sense. So we show that this proof holds. So we will prove this. And recall that here we are proving a lower bound on the least chromatic number. So that means we need to find the least assignment where the L, proper L coloring does not exist. So that's our goal. So what do? We take largest number S, which satisfies T over 4 is still bigger than S to the 4 choose F times log of 2 times S to the 4 choose F. So for small s, I mean, if f is small, this is smaller, but when you increase f, this gets increased. At some point, this gets bigger than this d over 4, but right before that, we take s, which verify it. Then from this, what do we know? Then this s is actually some constant times log d over log d. Constant C. Simply, I mean, you can estimate that if you, this is just computation, so I will not, show you the computation. Simply, you can check that when S is some small constant times log D over log D, and you compute it, and then this is smaller than D over 4. It's easy to check that. Take, say, 1 over 1,000 times this, and then you just plug in. And this is smaller than D to the 1 minus epsilon. So this is give you some polynomial, which is much smaller than linear polynomial D. So this is smaller. So anyway, so from this, what we know is it suffices to show that the least chromatic number of G is bigger than S, because S itself is already bigger than log D over log D. Okay? Like, so to make our analysis easier, we will take a subgraph of G. And if we know the lower bound on the least chromatic number of this subgraph of G, that is also lower bound on the least chromatic number of G. So if G has average degree T, it has a subgraph G prime with the minimum degree LXT over 2. So this was one of the homework problem. So you can actually prove it as an exercise. And again, this subgraph G prime has a spanning bipartite graph, bipartite subgraph. H such that this H has degree half of the degree of G prime for all vertex, so that its minimum degree is at least T over 4. So again, this is also well-known fact. You can try to prove by yourself. I mean, you have to try to take a vertex partition of G prime, which maximize the number of edges in between, and then delete all the things inside, then you get this H. And then it's difficult to check that this statement holds. Now we have this H. Now we want to, we now want to generate a random list assignment L for this H with all the lists have size exactly F. And then show that this assignment give us one assignment that where we cannot pick a proper alkaline. So we let A and B be the partite set of H. So we had A and then we had B. Say the larger one is A, larger or equal one is A. Then let the capital S be the bracket S to the 4. The numbers between 1 and S to the 4. And let T be the S to the 4 choose F. So now what? We first assign a random S set, S subset of size S of this capital S as its list independently, uniformly at random. So uniformly means that all T such sets equally likely. And independently means that the choice for this vertex and choice for the other vertex, they are totally independent. So now what? All the vertices B are even list, and A not yet. And we say that a vertex of A is full if all T possible KAIST appear on its neighbor. If this is the vertex and you have its neighbor, and then see what list you have, what list you have, what list you have, what list you have. And then here, all possible T sets appears at least once. Then we say this is full. Then what's the probability that given vertex is full? For that, I mean, if this is not full, there must be a certain set, say, T, and that does not appear any of them, right? And such a probability is that the particular set of size f T does not appear on the neighbors of this B is what? So the probability that something appeared here, which is other than T, is this. And then here, again, something appeared that's not T, is this, and so on. Then you have to multiply them because their choices are independent. So this is the, degree of this B. Okay, let's write it as F mod X. So this is the probability. But since there are T such sets, so the choice of such set is F to the 4 choose F. What do we know? The probability that the X is not full is by union bound and most T times 1 minus 1 over T to the EHF. And then what? This is at least E over 4. So if you, this is smaller than, so this is smaller than that. So this is, so this inequality, yeah, it's inequality holds, so you have this. And what do we know? This is what? T times, here this is E to the negative T over 4 T is an upper bound. And what do we know? We know that T over 4 is bigger than T times log 2T. That's what we assumed here. So this is T, this is T. And what do we know? T over 4T is bigger than log 2T. So this is what? T times bigger than, this is at most T times E to the negative log 2T. And what? This is smaller than half, at most half. So now let capital X be the number of full vertices in A. Then what do we know? The expected number of X. Expectation of X is each one, yeah, maybe. Let's write it as to make it clear that this is small letter X. And expectation is what? This is summation where X is the one indicator random variable if X is full. Otherwise it's 0. And what? This is summation of all vertices in A, the probability that the X is full, and that's what? Almost half times the size of A. And what? This proves that there is some outcome of the random list assignment on B such that at least half of the vertices in A are full. So, what? We fix such an assignment. L on B. So, now what? We have A, and then on B, each vertex you have its list assignment. And A, we haven't really assigned anything yet. So this vertex we have to assign list. But this vertex all are equipped with list. So now what? So these vertices are full. Now, what we claim that extending this by a random list assignment for A. So on A, we randomly assign this on the vertices again. That produces with positive probability. That produces the list assignment from which no proper coloring can be chosen. Again, we assign a set of size S as a list of these vertices independently and uniformly at random. So, now what? When we want to check that no proper coloring can be chosen, we first, what to show what? We choose one color from here, 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 one color from here. Then, for such a choice, we show that, okay, we cannot complete the coloring. So that's first choice. And then you choose another choice. From here, you choose. From here, you choose the color. And then second one, also not possible. And you do that for all possibility here. And if none of them can be extended to the proper coloring of everything, then we can actually conclude this, right? For that, we consider F the particular choice of colors from this 1B. Then what? For a full vertex X in A, what do we know? We know that all lists are here. Since all S subsets appear on its neighbor, you know that the most S-1 color fail to be chosen on its neighbors in this F. Meaning that, okay, you see the value of F. Its F value is a 1 here. F of A is 1, F of B is 2, And then C, what color does that appear? Okay, you choose, okay, so out of here in this F color, say 3 doesn't appear, and 5 doesn't appear, 7 doesn't appear, 6 doesn't appear, and you write it down. And if there are more than such a color, then what happens? This is the set of size S, but there must be a vertex whose list is exactly this. But from there, we choose one color as its value. That's a contradiction that this one was the value that never appeared. That means the number of such colors that's never appear is at most f minus 1. So, what? So in order to be able to color its list need to contain one of these colors. Otherwise, what? I mean, all the colors that appeared here are forbidden to be used here. So this list must contain one of these colors to be able to color. In order to hence, if f can be properly extended to this vertex x, only if this list of x, which we are randomly choosing, it contains one of these missing colors. And what? There are, so what's the probability that x can be colored? It's at most. So one of these, so the number of sets which contains one of these colors is this, right? So we don't know what these S numbers are, but one of them must appear, and then rest of them we don't care. And then you divide it by T, the total number of colors. And this is what? This is at most, no, this is actually exactly S minus 1 over S cubed, which is more than 1 over S squared. So this we know. So we didn't assign any list assignments yet, but once we assign it, the probability that X cannot be colored, assuming this F is already there, is at most this. So in order to extend its F to an L coloring, all full vertices must be colored. So the probability of the possibility of this extension is at most or less than but 1 over x cubed s squared to the a over 2, which is the number of, the lower bound of the number of full vertices. And this is what? S to the negative a. Now, how many F's are there? For each one of them, there are S colors, and you choose one of them, you choose one of them. So, yes, there are S to the B many choices of the coloring F on B from the given list assignment. On B, the probability that some choice of colors on B, coloring, some choice of colors on B extends to an L coloring is by union bounded by S to the B times S to the negative A. It's actually less than, because this is less than, which is M of 1. So, and what it means? Then it means that if we randomly assign these colors, this assignment on the A, and with positive probability, none of these choices of F extends. Hence, there is an outcome of the random list assignment to A such that no proper coloring can be chosen from the list. So this proves what we want. Okay, then natural question here is that is this best possible? So okay, we get that the chromatic number can be kind of independent on the average degree. It could be very arbitrarily smaller than our average degree, but this chromatic number must grow with the average degree. Then it will be best possible. And indeed, Alon later improved this, that the half times, essentially, okay, half minus 3 log 1 times log D also suffice. So this also holds. So we can remove log term, and this is natural log. And there is a conjecture that on the other hand, the conjecture is that every graph G, let's say, every deregular bipartite graph G satisfy that its chromatic number is at most some constant times log D. So this constant C is independent of D or G. So this is conjecture. But the best known bound is that it is at most some constant times D over log D. So there is quite a big gap. So if at most D is D plus 1 is easy, right? That's from just criticality. And this is only improved by multiplicative log D term, while the conjecture is completely, polynomial is completely one and only log. Okay, so that was one example of how we use this random variable. And yeah, maybe let me mention one inequality which is useful as a proposition. N should k is at most n times e over k to the k, and 1 plus x is bounded by 1 plus x. So these holds. So this will be useful later for our calculation. Okay, so we learned about this random variable and then how we use this expectation to prove what we want. And next time we will learn more techniques in progressing method. The next time we will learn about something called iteration method. That's what we will do next time. Okay, thank you for listening. I will see you in the next video.